Okay, continuing with our thermochemistry, this lesson is going to be on heats of fusion, solidification, vaporization, and condensation. We're going to start with fusion and solidification. Heat of fusion. Fusion is melting. So when 1 mole of a substance absorbs heat, then that substance is going to melt. It's going to be endothermic, and we're going to note it with delta H. So heat of, and then a subscript fusion. Heat of solidification is when a substance becomes a solid, so heat is going to be lost, therefore it's going to be exothermic, so it is the heat of solidification. So the quantity of heat absorbed by a melting substance is going to equal the quantity of heat that that substance releases when it solidifies. So the amount of energy you have to put in to melt a cube of ice is going to be the amount of heat released when that substance freezes. So the heat of fusion is going to equal the negative heat of solidification. Remember, when we are releasing heat, we're going to use that negative sign, but it's not an actual negative value. It's just a sign for us to know that heat is being released or energy is being released at that point. So if we have the heat of fusion of ice is 6.01 kilojoules, that's not going to change. It's always going to be 6.01 kilojoules per mole. How many grams of ice at STP could be melted by the addition of 2.25 kilojoules of heat? So we're going to start with our 2.25 kilojoules, and we're looking for grams. So we're going to have to use this kilojoule to mole conversion. Since we need moles to get to grams, we're going to put the 1 mole over the 6.01 kilojoules, and we need it in grams, and we are talking about ice, which is water, so we have H2O, so the mass of that is 18, so we're going to have 18 grams of H2O per mole. So 2.25 divided by 6.01 times 18. That means we can melt 6.74 grams of ice by adding 2.25 kilojoules of heat. Now continuing with condensation and vaporization. Vaporization is going to be the amount of heat necessary to vaporize. So you're going to have to put heat in to make this liquid become a gas. So therefore it's going to be endothermic. And that's going to make condensation exothermic. The heat's going to be released as those gas particles come closer together to make a liquid. Again, energy is conserved, so your heat of vaporization is going to equal your negative heat of condensation. Not sure why I just did that. But here's our example. Heat of vaporization of water is 40.7 kilojoules per mole. How much heat is absorbed when 24.8 grams of water at 100 degrees Celsius is converted to steam at 100 degrees Celsius? Remember, water's boiling point is 100 degrees, so that's where we're getting this value from. So they are starting us off with 24.8 grams of water, and they want to know how much heat. So our unit here is kilojoules per mole. That means we need to turn our grams into mole. And from there we can use our 40.7 kilojoules per mole to get to our kilojoule answer. So 24.8 divided by 18 times 40.7 to vaporize 24.8 grams of water. So if we look at this chart here, you can see the relationship between our states of matter and the phase changes that are occurring. So here's our enthalpy down here. We're at a low heat exchange. Solid is condensed. And as you add heat, you begin to melt. So that is our fusion. You keep adding heat. Heat of vaporization is going to have a higher value. This is going to take a lot of energy to get to that vapor. And as you go in the reverse direction, as you cool down, you're going to release the same amount of energy that had to be put in to get that substance back to a liquid. And the same thing goes for a solid. The amount of heat that's going to be released to cause this substance to solidify is going to be the same amount of heat that you put in to get it to melt. So that brings us to a heating and cooling curve. This is going to be a graph of temperature versus the heat being supplied. And it's going to tell you how much energy is required to go from one phase to another. So those arrows, we're going to get values for those. So this is a heat curve. This is the heat being added. So as we go in this direction, we're adding more heat. This is our temperature on the y-axis. So as you add heat, temperature goes up. Our three phases, here's our solid, here's our liquid, and here is our gas. And then this is where our phase changes are going to occur. And you'll notice that for our phase changes, the temperature does not change. The temperature is staying the same at our phase changes. The only time we're having a temperature change is when we have the kinetic energy here and when heat is actually being put into the system. So here we have our kinetic energy, so it's absorbing this heat. It's now going to become a solid here, and it's storing that energy. It's using that stored energy to go into the next phase. And so here we are at our liquid. So as the heat is added, it's absorbing that heat until it gets to its boiling point here. And then that's when it's going to become potential energy and it goes through its phase change. Please make sure you draw this heating and cooling curve. You are going to need it and be able to identify points on it.